Welcome back, students. Today we're in lesson 20 and we're going to review the product of square roots theorem. And all that says is that if you take two square roots and multiply them times each other, then you can get a product underneath the same radical symbol. And conversely, you can do the inverse and you can take a factored or a multiplied product under the radical and factor it out into individual radicals so that you can simplify. They mean the same thing. They're the same number. So you're going to want to write that in your notes. And let's move on to 20.1 to illustrate this a little bit better. Sometimes this theory is great, but it's when you see it applied that it really makes sense. So we're asked to simplify 3 times the square root of 50 minus 5 times the square root of 200. Okay, we can't do anything with that as it is, but we can factor these out and simplify them so that we can. So the first thing to do is figure out if there are any squares in here that we can take out. So let's make a factor tree for 50. So we have 50, and we know that 50 is 2 times 25, right? And we know that 25 is 5 times 5. So we can take a pair of 5s out, and we have 2 left behind. So 5, which is our pair here, 5 times 3 is going to be 15, and we're left with the 2, so that's times the square root of 2. And that's as far as we can simplify that one. So let's look at this radical here. We have 200. Let's do a factor tree for it. We have 2 times 100. We know that 100 is 2 times 50. We know that 50 is 2 times 25. And we know that 25 is 5 times 5. All right, so we have a pair of 5s. And we have a pair of 2s, right? And we're left with a single 2 behind. So 5 times 2 is 10. So 10 times 5, our constant here, is 50 times the square root of 2 is what we have left. Now we can perform this calculation. 15 minus 50, that is going to give us a negative 35 times the square root of 2. And that is our answer. Okay? So we can see how this helps us to pull these factors out. And let me write it the way that the book has it written. Just to illustrate that point, we can say that the square root of 50 is equal to the square root of 2 times the square root of 5 times the square root of 5. That's literally what we have here, because 5 times 5 is 25, and 25 times 2 is 50. And we know that when we have two square roots that multiply by each other that are the same base, that we can pull that out as a whole number constant. And that's what we did. We eliminated those and brought that out as a 5 times the square root of 2. And because we already had 3 times the square root of 50, we were able to calculate and say 3 times 5, and that left us with 15 times the square root of 2. You see how that works. Sometimes it helps to visualize the square root symbols. So if that is what helps you, then you can do that. And again, with 5 times the square root of 200, we'll visualize that for you. We have 5. And then we had the square root of 2 times, and then we had 100, which was 2 times 50. And then we had 50, which was 2 times 25, and 25, which was 5 times 5. So we were able to pull this out. So that's a 5. And we were able to pull this out, which is a 2, which left us 5 times 5, which is 25 times 2. So that's 50 times the square root of 2. And that's what 5 times the square root of 200 is equal to. If the illustration helps you to see it better, then use this illustration. I like the factor tree just because that's what I was originally taught, but this is the same as the factor tree. It's just written a little bit differently so that you can visualize the multiplication of these two radicals canceling each other out and turning into a constant. Okay? And that's what happens. So if you think about what this means, then you know that the two together makes the constant. All right, let's move on to 20.2, which is the same thing. I'm going to clear this page, so pause and take notes if you need to. 20.2 asks us to simplify this problem. All right, so the first thing to do is the multiplication. Let's just go ahead and knock that out. Oh, I'm sorry, there's a 2 here. I thought there was another number. So let's do the constants first. 3 times 4 is 12, times 2 is 24. Now we can do the radicals. 2 times 12 is 24. And I'm just going to write this down here because I think this would be easier. We don't even need that, do we? We just need to write the radical. So instead of multiplying them all together and then factoring them back out, let's just leave them unmultiplied and break this one down. So we have 24 times the square root of 2, and we can factor this one as the square root of 2 and the square root of 2 times the square root of 3, and then bring down our other square root of 3. Because we know that 12 is 4 times 3, right? Well, now we see we have some constants or some factors we can eliminate into a constant. So we have this becomes times 3, and then we can eliminate this becomes times 2. So we can say that 24 times 3 is 72, and 72 times 2 is going to be 144. So we have 144 with a remainder here of the square root of 2 as another variable. And that is our answer. Simplifying these radicals gets pretty straightforward and pretty easy once you practice enough of them. We have one more, 20.3. Should be pretty simple for us to do. This is a distribution problem. We have 4 times the square root of 3. And that is times the sum of 2 times the square root of 3 minus the square root of 6. So we're going to multiply these. First, we're going to do the constant. That's going to be 8. And then we have square root of 3 times the square root of 3, right? Minus, and we have 4 times, this is an imaginary 1 right here. So that's 4. And then we have the square root of 3 and the square root of 6. These cancel, and we can say 8 times 3 here, so that's going to be 24. And here, we know we can factor 6 into, let me change that to the square root of 3 times the square root of 2, right? So these two will cancel, and we're left with 4 times 3, that's 12 times the square root of 2, because that's our remainder. Does everybody see how we did that? Pretty straightforward, but that is our solution. All right, moving on to parallel lines to a given line. So some more linear equations and y-intercept formats. So I'm going to clear the page, take notes if you need to. And let's move on to, I'm going to go to some grid paper here. So we can tell if lines are parallel by looking at their slope. So in this instance, y, let me write this in the right color, that'll make it a lot easier. Y for the red line is equal to the slope of 1 over 2x plus 2, because our y-intercept is plus 2, right? Our slope is 1 over 2. Now in the blue line, we have y equals 1 over 2x, and we can see it's negative 1, right? And in the black line, our slope is 1 over 2x, and it's a negative 4. We can tell that these lines are parallel because they all have the same slope. The only thing that's different about them is where they are laying on the Cartesian coordinate system, and that is determined by their y-intercept location. So we have the 2, the negative 1, and the 4, but in every other regard, they are parallel to each other because they go up 1 and over 2, up 1 over 2, up 1 over 2. So you can tell if a line is parallel just by looking at the slope of the line. If they have the same slope, so lines with the same slope are parallel. That's something you need to write down in your notes. Okay. And so we are given a problem to solve to see if we can create that relationship between a point and a given equation. So we are going to try 20.4. And we are asked to find the equation of the line that is parallel to 2y minus x equals 2 that passes through point 3 and negative 1. Okay, so first we have to put this in the proper format. So we're going to solve for y. So 2y equals x plus 2, right? So now we're going to divide. We know this is a 1 right here because every variable has the invisible 1 if there's no constant there. So when we divide everything by 2, we end up with y equals 1 over 2x plus, and 2 over 2 is just 1. So this is our equation of the line, our linear equation. And now all we have to do in order to create a line that has a parallel, that is parallel to this, is to take this point and substitute it in for the x and the y values. So all we have to do is come over here and say y is negative 1. So negative 1 is equal to 1/2. We put the slope in, and x is 3. So we put 3 in here for x plus 1. Okay, so now we solve. That's all we have to do. Actually, we'll take b, we'll take this out because we don't know what the y-intercept will be just yet. So we put b in here, and then that will tell us what the y-intercept is, because if we give it the same y-intercept, it's not going to be parallel. It's going to cross over. So we don't know where it's going to start, but we do know what point it passes through. That's why we can sub in here. So let's solve. Negative 1 equals, I'm going to put this over 1 to make it a fraction. That's going to be 3 over 2 plus b. Okay, now we move this over and we say negative 1 minus 3 over 2 equals b. So we make that a fraction. We know we have to multiply this in order to make it a fraction we can use. So we multiply both by 2 to get the same denominator. So that becomes negative 2 over 2 minus 3 over 2 equals b. So now negative 2 minus 3 is going to be negative 5 over 2 equals b. And that's our y-intercept. So our slope of the line that is parallel to this is going to be y equals 1/2 x minus, because this is a negative, 5 over 2. And these are our two parallel lines. And that is correct. We know they're parallel because the slope matches. That's all that has to match is the slope. The y-intercept for this line is +1, which would be right here. And the y-intercept for this line would be -5 over 2. That's going to be -2.5. So it would be right about here. Okay, two parallel lines. All right, and if you wanted to, you could try that out by graphing it to see that it came out the same, but I assure you they would be parallel lines because the slope is the same. And we have, that's it. That's all we have for lesson 20. So I'll see you in lesson 21.